Well, thank you very much, Bernard. Thank you for the invitation, the opportunity to be here. Also want to thank Jorge, who was very helpful in helping me set up things. Thanks everybody for being here, attending this talk. And so this is, as I was telling Bernard, a very nice thing we're experiencing, right? At least from this bad moment, which is these remote talks. And it's nice to see that, Bernard has had this for more than 5 years. And actually, this subject, I came into this subject in 2011. I want to say a little bit about how I got into the problem. I didn't know there were so many, say, problems, interesting problems beneath rotational waves. So this started when I went for the first time, actually, to the Schrödinger Institute for a workshop, Vienna 2011. And it was a meeting that actually was organized by Davi Lan, who invited me. He had been here in Brazil and then so on, and also by Adrian Constantine that I had never met. I met him for the first time, of course, I had heard of him. And at the very end of this meeting, it was very nice. And that's how the story started, that Adrian came and said, look, I've been working on these problems, and it would be nice if more and more people get into do computations and so on, because, he's proving theorems, a lot of very nice work with Walter Strauss and other people. And then he said, it would be nice to have computations with precise locations of objects of interest. And he mentioned some to me, which I'll show you, things basically beneath water waves. And actually, also he gave me the paper of a person I knew. It was very nice. Teles da Silva is a Brazilian, Fernando Teles da Silva, that unfortunately passed away more than 10 years ago. I knew him, was a good friend and so on. I knew he had worked with waves and vorticity, but I had never really known the importance of his work in looking beneath the waves. And this was fascinating to get in. And I had a student who was about to start his thesis, was about to do qualifying Roberto, that's one of the co-authors. And I said, well, let's get into this. And he said, yes. And Adrian said, look, let me give you hints of things that you should look for. And so we started getting educated in the problem. And let me start with something very simple for those who are not from this problem. So this already is something very, very interesting, which is you start with linear waves. And what I'm going to be doing, many people here actually attending have done very nice work looking beneath rotational waves, looking at the phase space sort of structure that stream functions give you. But from the things that Adrian pointed out to us, we actually not only looked at that, but also looked to the ODs, basically what I'm going to be calling the particle dynamics or the submarine dynamical system, which is this dynamical system here, which for linear waves is already quite non-trivial. And why? So these are maybe for people who are not from the field, is that if you take and do the linear problem, do like just separation of variables, if you have like a wave that is a single Fourier mode, and you do its harmonic extension inside the domain where you're going to be solving Laplace's equation, you see up here, the vector field is quite nonlinear. And if you expand the Taylor series expansion near the point and so on, then you find that the particle orbits are these ellipses and so on, and depending on the regime, it goes to circles and all these things that we know. And actually, when you see sometimes in some lab experiments, they look like closed orbits, but actually there is always a little bit of a Stokes drift because of this, when you do not do this approximation. So therefore, this is where the story really starts with Adrian. At the time, he did not have this paper. It was 2011. And here's the Stokes drift. This is a nice sort of a topical review. And then Adrian had just some time earlier proved, which means things regarding orbits of particles. And the first thing he told us to maybe try to find numerically. So I broke this up into part 1 and part 2. So 2 problems that not quite at the same time Adrian was saying, hey, why don't you try to do this numerically? Is first to find for irrotational waves closed orbits as predicted by this paper by Adrian with Walter Strauss. And it's something sort of intuitive to some point. If you think about it, right, you have this loop, this Stokes drift. And if you have a current, actually a minus kappa, this sign, it's kind of, maybe you might think, well, it might close into a closed orbit, right? Will compensate the drift. That's intuitive, but a theorem and a proof up to, as you see in the paper, only came quite recently. This is for I think the nonlinear case, then I had in the previous slide, the one for the linear case and so on. And then Adrian said, let's see if you can get a nice method to find where these guys are, right? I mean, they proved that there are there can exist closed orbits and so on. So this was our first exercise. Let's try to hunt for getting numerics to these guys. And I started getting fascinated. Many things I did not know. And you see, you open this door and there's so many nice problems. So this started work with Roberto Ribeiro. Here was my student. And later on, Paul, I was at Bath, and Roberto came and visited, and Paul was very important getting into the picture. So the first exercise is then, let's find the closed orbits. And actually gave me an opportunity to use something that I had learned some time before and never really used it. I'll show you just in a few slides. So here is a little bit of the display, the shopping window that Adrian was showing, all these type of loops, all these types of Stokes drift, depending on the direction, not only of the current, but also where you are beneath the wave. And there was the existence of this closed loop, this closed orbit. And this closed orbit is in the fixed frame. We're going to be doing simulations showing things both in the fixed frame, and most of the work that people, like I see Katie is here, done some nice work and so on, is in the moving frame, where the wave then becomes stationary. The traveling wave, the Stokes wave, becomes stationary, and its free surface is a streamline and so on. Okay, so this one we have to look in the fixed frame. And actually as I'll show you one simulation, we actually found these also non-smooth trajectories that were not sort of mentioned before, but they're basically a limiting form of these loops here and these loops here, when the particle is sort of going up and is going to form the loop, then boom, the wave brings it down and does not form the loop. So, okay, just a curiosity, nothing that important. So let's go and see how we formulated the way we started hunting for this guy, and then for stationary points, we're going to do it in a different way. So many of you know very well, John Carter also gave a talk yesterday, very nice and so on. So potential theory for water waves, here is the velocity potential, the velocity field, the free surface conditions, Bernoullian kinematic condition, Laplace, Neumann at the bottom. It's basically, we're considering at first incompressible irrotational flow. And our goal, right, since we want to do the submarine dynamics, as I like to call it, we have to find the vector field for this simple looking dynamical system, but as I mentioned, highly nonlinear, even for linear waves. So our goal is to find, nice wave, this dynamical, the vector field, sorry, for the dynamical system. We're also going to display the stream function level curves and so on as people do. So here was the first fun part for me with using boundary integral formulation, and I'll tell you why I thought it was fun. I said, Roberto, let's try something I always had in mind, which is this. Here we have Green's third identity. So basically, this is Green's identity, but now with the Green's function. You can use the free space Green's function, but there was a Green's function that I had sort of learned, saw this expression sometime before in a nice talk about Dirichlet to Neumann operators, which is the following: a periodic Green's function that will erase the boundaries of this periodic cell. We have a periodic wave, Stokes wave, so in a periodic domain, we want to find the closed orbit. So this is what happens. As soon as I use this periodic Green's function that was in this paper by Patrick Guidotti, Journal of Computational Physics 03, plus the method of images, I erase the bottom with the periodic Green's function. These two contour lines cancel each other. And then, as Adrian jokingly told me in 2011, saying, I'm trying to convince some people to dive, looking beneath waves and so on. Well, here's one that you don't even need to dive. You can sit in your boat and using properties of the elliptic part of the problem, right, of the potential theory, you know everything underneath you, if you're lying here in the free surface, because of the Green's third identity. So the expression ends up looking like this. So the vector field, which is the speed, right, at the position of the particle, say one component, which is u of x, y, is given in this way. Kappa, as I remind you, is the current, the constant current. It's given by this integral. Messy looking, doesn't really matter that much, and so on. And even for the linear problem, we sort of evaluated also over the free surface. And this is important if you're looking at a particle very close to the free surface. But the nice thing is that we're up here. The integrand of here is actually a periodic function, which is smooth because the Green's function blows up only inside, right? I mean, the source is inside, or the source is on the free surface, but we're looking inside. I switch things. So trapezoidal rule gives us spectral accuracy. So we have something very accurate, just integrating over the free surface. And yes, oh, and that's how we compute it. And here's the closed orbit up to many digits of accuracy. Here is the orbit in the fixed frame. So here's an animation for the orbits, many points below the wave in the fixed frame, and it depends very much where you start to see the closed loop. So here you see a little bit of a Stokes drift backwards. Here you see Stokes drift forward, right? And actually you see that this goes, I think it's mentioned in the papers by Konstantin and Strauss, this goes sort of along a streamline, basically sort of a fixed distance, from the free surface. And here we can actually see that. Oops, why is it not running? This is strange. I apologize. Let's see if I can fix this. No. Well, I don't know why this is not running, but I get, I don't want to waste too much time trying to fix this because there's more important things afterwards. But these are exactly along streamlines following the wave. I don't know what I am having problem with this. I apologize. So, okay. So then we go to problem number 2. So problem number 2 is waves with constant vorticity, as many people here present studied. So we're going to try to look for precise positions of stagnation points. We're also going to look at the phase space structure, and we're going to look at pressure anomalies to start with. So this, Paul came in, was very helpful, many ways, things that he had experienced. So here we change the strategy and we'll use conformal mapping to flatten out the free surface. So before we do that, we know that when you have constant vorticity, you basically can break up the problem and solve for the harmonic component of the velocity field. So again, you're back to Laplace equation, you're back to using properties of harmonic functions and so on. And that's how we do. So we're going to have the vorticity, we're going to have this part, which is the harmonic component of the velocity field. This psi tilde that appears here is not the stream function. It's actually the harmonic conjugate of the harmonic part of the velocity field, the Bernoulli constant, and so on. So we're going to solve using the harmonic structure of the problem and using conformal mapping, as I'm going to show you in the next few slides. So here we're going to also, at some points, I'm going to show you numerics. It's important to put yourself in a moving frame. So we don't know the speed of the wave, but it will be found through Newton's method. So this is basically the free surface conditions written in the moving frame. Again, the harmonic conjugate. Here's the expression for the pressure, which eventually we're going to use and compute. And how do we then do our numerical setup, which means with the conformal mapping and so on. I'll show you in a second. First, let me put some of the results from previous work, which guides us into looking for things. So some interesting numerical papers that many of you know, and we also know, we learned about these papers as we know. So it's basically numerical results, as I said, without particle dynamics, but looking at the space of the phase space pattern with streamlines, which for a steady, basically traveling wave is basically an excellent way of doing things. So there's a paper by Teles da Silva and Peregrine that points out many things. They do it through a Cauchy integral formulation. There's a paper by Coe and Strauss that use a formulation that is very keen, I think, for proving things. So that analysts use this equation very much, which is the de Broglie-Jacotin formulation, a kind of a Hodograph transformation. And there is also the very nice formulation, the AFM, Ablovitz-Focas-Muslimani formulation that Bernard, Katie, Vishai, many of you have used, and it's very nice. So from the paper of Teles and Peregrine, and many of you that have looked as well, we see where where we have this sort of recirculation region, which is basically, which will give rise to, say, Kelvin's cat-eye structure. And we have, in this case, 3 stagnation points, right, that arise. And there's actually a case which was already mentioned here in the paper by Teles, Da Silva, and Peregrine, which is if the vorticity is high and this streaming over here is very strong, you can get the pressure here to be actually below the atmospheric pressure. So there's a point here where the pressure is small, and actually there's also other anomalies like the high pressure being below or near the troughs and so on, as for example pointed in the paper by Katie with Bishai. So basically, a way I like calling this, which is how my intuition works, and I mentioned many of you, is that this recirculation zone here, region, in this moving frame, the wave is stationary, basically it looks a little bit like a hydrofoil. So basically one has that eventually here with this high speed, you get the low pressure, and actually the stagnation points here below, you're gonna get the high pressure points. So this is some figures from the paper of Katie with Vishal, and pointing out exactly this maximum pressure, this pressure anomaly, maximum pressure, not below the crest, but away and actually close to the trough. And actually one, with the PDEs, one can push this to be exactly below the troughs. And then there's also this very more recent paper, theoretical paper by Konstantin Strauss and Barbaruka, proving things where I want to point out something that actually in the recent paper, referees were getting a little confused, and it's important. I think we had to express ourselves more properly, is that actually here they have the vorticity in a different sign than the way I'm using here, but is also about the critical layer. So the critical layer, and there's basically, there's no collision between the ways of thinking it, but some papers, one would say the critical layer is this line here dividing the flow, say, to the right from to the left. And in other papers, the critical layer is actually mentioned as the region with closed recirculation zones. So that's why I'm highlighting with this sort of yellow thing. And maybe to avoid the definition of critical layer, which the one with the recirculation zone, I'm going to later on in this talk, a more recent work, mention about the Kelvin cat-eye structure. So we're going to be sort of looking at that. Okay, so our formulation is basically has been used by other people in other papers. Choi, Milewski, Van den Broek, and Zan use this formulation. Actually, the conformal map is also been used by Konstantin and Barbaruka. And basically the way to think of this is basically it's nice to work in this uniform strip, because in the uniform strip you can do all the harmonic extension of things quite more easily using Hilbert transforms, say, on the strip and so on. So the situation is basically I have my wave elevation in this canonical domain of the conformal map. I'm going to call it bold Y. This is, of course, the Dirichlet condition for this map. This guy's going to go over here. We have this condition here on the bottom. And we decide in our formulation that we're going to keep the wavelength the same. So here and here. And therefore, the depth, because it's a conformal map, the depth is an unknown because it depends on the wave height and so on. So we're going to have a few things to solve for in a Newton's-like manner, which I'm not going to show any details here, but just you can see to one of the references I'm going to mention. So as soon as you have this Y, as soon as one finds this Y through this sort of a Newton iteration, then you have everything, because this is like a simple Laplace problem you can get inside using Fourier integrals. You can get the map and you go through. So just as a snapshot of what we do, you can rewrite Bernoullian kinematic in one equation. There's this ugly looking guy here. And with this ugly looking guy, we have to identify the things we don't know. The things we don't know is, of course, the wave elevation in the canonical domain, the depth of the channel, as I mentioned, because I'm asking both domains to have the same period, the Bernoulli constant, and the wave speed. So basically with the Newton continuation method, plus 3 supplementary conditions, which is an expression for the depth you get out of conformal mapping, we ask for a given wave height, and we just say that the level is, the wave is such that you have a mean zero profile. You crank up this method and you get these guys. Once you get these guys, you're good for then solving your problem numerically. You have these Fourier integrals here, as I mentioned. So as soon as you have the Dirichlet condition on the top, you know this harmonic function, which is the imaginary part of the conformal map. Because of Cauchy-Riemann, whatever, you get also this part, the real part. You have the map, and also you also have to get your initial conditions for your potential, because we have potential theory. And you crank the wheel. This is in a JFM paper 2017, and I realized later on it's very similar. I think something that Sergei Dyachenko and Vera Hurd that also, I mean, many people do this in a similar way, looking for hanging profiles, overhanging profiles. You get here these guys in terms of the bold Y, and you can then decide to solve again. Now going. So here's the Hilbert transform on the strip, as I mentioned, and then our goal at the end is to do these orbits for particles, the submarine dynamics. We need to get the vector field for our ODEs. And actually we played with both, which is basically solving for the orbits in the physical domain, like this, basically doing just the change of variables, or actually computing them in the canonical domain and then mapping. And the same thing for the level curve for the stream function. So both ways kind of work. And this is, as I mentioned, is basically our goal in terms of having the vector field for our dynamical system. Okay, so also our goals was then to be able to compute the precise location of stagnation points, critical layers, particle trajectory, moving and lab frame, pressure anomalies, and other things. So here is a snapshot of the streamlines, as shown very nicely in other papers. So this is basically what I call the phase space sort of streamlines. You see here the recirculation zones and playing with parameters, right? With vorticity, sometimes playing with steepness of the wave and keeping the vorticity fixed, but this is actually playing with vorticity. You can see that actually you can have 1, 3, or 2 stagnation points. And soon I'm going to show you a nice animation Roberto did, where you animate things in vorticity. So basically, as vorticity sort of starts growing, you don't have a stagnation point. The first stagnation point pops at the bottom. It breaks up into 3 and so on. Like here, it has 3. And here, basically, you have only 2 stagnation points because this guy here is the same as the one that would be here. So over a periodic window, we have 2. And here's the formation of the Kelvin cat-eye structure. So in the next slide is the animation, hope it works, of, as I mentioned, the animation using vorticity. So as we crank up vorticity, so here there's 0 vorticity. As we crank up vorticity, you're going to see a critical point appearing right below the crest. So here we have 3 profiles of Stokes-like waves. And then you crank it a little more, it breaks up into 3, and off it goes. Okay, so it's going to work. So here it is. 1 point and 3, a little recirculation zone. It starts growing, and it stops basically when it hits the border of the periodic window. If you increase vorticity, the animation didn't have this.
Talvez não precisa nem ser tão aplicado à engenharia, mas que seja algo que eles possam entender a palestra, né? Usando realmente como você falou,
Marcelo, tô te ouvindo, Marcelo, por favor. Marcelo.
Geometria.
So, sorry. Hello? Can you hear me? Okay. So, so here's basically the recirculation zone, and how it varies with vorticity. Okay. Now this figure, I also like it very much. First time Roberto, I think, did this. It was in Bath, where I was spending 6 months visiting Paul, and it's very nice because you're going to see now the submarine dynamics in the fixed frame and in the moving frame. In the fixed frame, it's basically, of course, a mess. But there's one thing that's nice. You're going to see that the particle that we put exactly on the stagnation points, the critical points, it moves horizontally, which means it's moving with the wave speed. And all the other ones are doing a mess. Whereas the ones in the moving frame, you're going to see the particles basically tracing the level curves of the stream function. So good, it's going to work. So here it is. So here, see, this guy is a critical point. It's moving exactly with the speed of the wave. And here you see actually how the guys actually on top of the, what I call the hydrofoil, are really moving with a high speed, and points very clear at the critical point, barely, the speed decreases. Let me run this again. And this at the critical point basically doesn't move. This one we put very close to the saddle point, so it starts moving very slowly, accelerates. So it's really nice to see, and it's really beautiful how, you know, people who started doing the analysis of this problem and so on, and figuring out these things, that, you know, this beautiful structure that is seen in the moving frame with the wave. And that's why the stream function is a very good object to use, including the Breuer-Jacotin equation. The change of variables uses the stream function. Here are now level curves for pressure. So here is when we have the smaller version, not so small, of the recirculation zone, and here are the points of maximum pressure, as was already displayed in that figure I showed from the paper of Vassan and Oliveras, and as sort of conjecture from Peregrine and Teles da Silva. And as the recirculation zone increases, you see these guys end up moving towards the trough. And here's already a point which is a minimum pressure inside the domain. And actually, if you keep on cranking this, I mean, I don't know if these things, I confess I don't have an idea of whether these things can or have been observed in a laboratory. In particular, you cannot, I know, maintain the structure, of course, because of other ingredients. But through the PDEs and through the numerical method, you can get these points to actually get closer and closer to the trough. So these are what was basically the pressure anomalies already highlighted in Teles da Silva and Peregrine's paper. Now, out of what we did, as I said, it was motivated by questions that Adrian was asking of precise locations. Could numerics find this, and so on and so on. So we had this already. This right, tested ourselves, learning with solving the submarine equations and so on. So we also, then I proposed to two former students, Roberto teaming up with Marcelo Flamarion, which is, let's look now, let's see what we can do for these kind of waves, look at the submarine dynamics in the presence of topography. My work, topography, always appears, it's always fun and so on. And we started trying things here and there and whatever. So because of instabilities with nonlinear traveling waves, and there's nice papers, right? Recent papers by Francis and Karif, among others, and a very recent one by Woo-Young Choi with Sunao Murashige, looking at instabilities and so on. We then said, well, let's try this thing first because it hasn't been done. Let's try this with linear disturbance. And actually, we're going to now look at what we're going to be calling, this is a very recent JFM paper, came out this year. So a time-dependent Kelvin cat-eye structure due to current topography interaction. So basically, we want to see the robustness, say, the persistence of the Kelvin cat-eye structure when the wave goes over a topography. And then later on, also, we want to see the Kelvin cat-eye structure emerge out of nothing because we're going to have a current or a flow interaction or vertical interaction with the topography, so there's no disturbance at first. So I'll show you these these results. So now the thing too that was fun doing is that, okay, we started figuring out things we had to do with linear waves, so we could get something that looked more or less like a traveling wave, because we have at start weak dispersion, so it's not going to be exactly a traveling wave. And we have a regime which is basically now non-stationary when the wave interacts with the topography. So therefore, the ODEs are not going to be autonomous, and actually stream functions, streamlines will not be helpful. They're helpful in some way, instantaneously, and actually they help finding places where to put the particles, but we cannot see what's going on just with the stream functions. So here's a snapshot of basically a case where basically it's nearly stationary, as I'm saying in the bottom. So we're looking at the streamlines, because there's a very weak dispersion, and actually it's kind of cute to see, if you let this guy go on, these little mini Kelvin cat-eyes start popping due to dispersion, due to the oscillatory tail that forms behind the wave that's going this way. And we have this sort of modulated wave, And now we have to put a very long domain too because of reflections and so on. The periodic condition is only for numerical purposes, right? We don't have anything that's truly periodic. Okay, so I think I already mentioned some of the things I have here, but let me mention again, which is basically the Kelvin cat-eye structure is now studied through path lines and not streamlines. And our dynamical system is basically not autonomous anymore. So now, this is what we're going to show. This is in the lab frame, so we're going to have to do now path lines, particle trajectories. So this is a little bit of a craftsman's work by Roberto and Marcelo, looking at the streamlines, tuning things, finding where to put the particles so we can see the things we want to see. So basically, there's like 80 tracers, whatever. You got to solve 80 times the submarine ODEs and so on to see what's going on. And so upstairs, there's the particle trajectories in the lab frame, and down here in the moving frame. So first, since we knew this, we started with the wave far away from the topography, and we're going to see something that basically we had seen before. And also because it's very time consuming and so on, this little sort of snowman almost that you see here would be just one eye of the Kelvin structure, and we're going to be following this guy, and of course to see better, zooming in this inset here. So let me release. Oh no, it's not working. Oh, this is a shame. What? Why some work and some don't? Oops. Why this does not work? Let me go forward, and then if I have time, I'll come back to this and see if I can show you this outside the keynote. Let's see. I don't know why. Oh, anyway, I'm sorry. No, I hope the other one works, or else this is going to be a pity. I do not know. Well, let's see. I'll try to, in the interest of time, let me go forward, see if the next one works, and I'll have to go back and try to find this outside. I wasn't prepared to have this outside, but I'll try to get it. So another thing we tried, so we wanted to do was based on another paper, recent paper related to Marcelo's thesis, which was co-advised with Paul. Marcelo spent some time at Bath, is waves generated by a mount, problem that is highly studied by many people that we know, using KDVs and so on, now with a sheared current. And one thing actually in this paper, which is basically we don't dive, there's no submarine dynamics, and was nice to see is actually that the vorticity for the waves generated from rest, the vorticity affects a little bit what would be the critical Froude number. So depending on the positive vorticity, the critical Froude number is smaller than 1. And for negative vorticity, which is basically an upstream one, it's basically downstream, sorry, the Froude number is basically higher than the critical one, and these are the typical patterns and so on. So we basically, this was another good way for us to test things in the non-stationary framework. Let's see if this works. It doesn't. So I'm in trouble because all my graphs now, this one also.
André.
Yes.
André, try to press the play on the top of the window.
Okay, let me try now. Maybe
the
with
play on the top of the window.
Yes, because the play was not working before. Okay, yeah, I got it.
Yes, press the play there.
Okay, good idea, Roberto. No, it's not working. It's not working because of the screen, sharing the screen. It worked before. I mean, let me see now. What's the idea of this? Well, but the problem is that I'm going to have to leave this screen and share another one. That's why probably it's not. I'm in trouble here. This is unfortunate. I thought I had tested this with Jorge before and it worked. I really apologize for this. So what happens is that, let me say what happens and then I'll try to fix because I'm going close to my 40 minutes time. So let me say what happens, right? And hopefully I'll see if I can share, or I don't know how I'm going to do this, but anyway. So what happens is that for this wave here, the wavelength is kind of comparable with the wavelength of the bottom, right? We did this a little bit on purpose, and it's very nice to see that this Kelvin cat eye here will sort of, now let me do with my hands due to technology problem, it would kind of be snaking like this over the topography without losing its integrity, and just basically following very nicely the structure of the bottom. And basically that's what I mean here by structure integrity not lost. So this works very well. We also tried, I was not going to show in the talk anyways, one with the rapidly varying topography, which also we have experience. And with the rapidly varying topography, it does not snake. And also you see particles all over. So there's something about having material curves or not material curves, because you see these guys crossing. And here you actually see this thing that looks a bit like a material curve, like snaking over the topography. Over here, then let me tell the story. Unfortunately, the videos are not working. Is that here now we have the flow starting from rest, and then from this sort of craftsman's work by Marcelo and Roberto, they put the particles, the tracers, where they know what's going to happen, right? So the wave now starts forming very quickly above the topography. Part of it moves away, and there's a part that sort of remains because of the regime of the fruit number. And you see these particles, now I have to use hands to animate things. You see these white particles. First, they're like shaking, right, jumping around. And as soon as the wave, because it's falling, it's in the wave frame, as soon as they're shaking up and down, but as soon as the wave starts leaving the topography, they really start forming a nice cat eye that moves together with the wave. And the last one, which also doesn't work, I don't know why. I mean, all animations were generated, I think, with the same kind of software, the same format. But here is basically then, because we know from the KDV problem, right? There's Grimshaw, Jean-Marc Vandenbroek, Atlas, many people playing with, many other people playing with forced KDV equations. One knows that actually in a certain regime, you have the topographic forcing is actually the same as a pressure forcing. And actually you can make the two of them cancel and so on. So here then, instead of the topographic forcing, we put a low pressure that sort of sucks a little bit the free surface up. And what would be seen here, and unfortunately one cannot see, is that a pulse forms, two pulses are emitted and go away. This pulse, due to the persistent low pressure, sits there, and a cat eye forms and sits, a single cat eye, in this case, we don't have to follow a single one, it's just one forms and sits below the pulse, and these are the particles showing that. And then finally, let me see, I don't know if I'm going to be able, because of the screen sharing, get this animation. Now, again, I apologize to all of you, but in our paper, actually, the one thing I might say is that in our JFM paper, there is supplementary material, and you would find these animations there. And finally, let me sort of advertise something which is a recent work submitted by Marcelo and Roberto by themselves, where using all this technology they got together from both of them, their theses and so on. Roberto was doing things in the fixed, for stationary waves and diving. Marcelo was generating waves and so on. And now, and with putting pressure. So basically, in their study now, they get a situation where they're using Euler's equation potential theory. So they have this paper on arXiv that's submitting, where they have solitary waves trapped in the low pressure region. So this is a single pulse here trapped in this low pressure region, and eventually it escapes. There are several scenarios that's described, and there's a very nice animation that they also, here I don't have the animation, but that they also put as supplementary material in their paper. Hopefully it will be accepted, we'll see, where they have 3 solitary waves trapped for a while in this low pressure region in darker blue, and for a while in the following sense. It's very nice. I mean, they collide, they go back and forth, one bouncing, the other one collide. Eventually, one comes here to the side like this one. It doesn't escape. It actually goes to the side and it's pushed back in, but then it bounces into the big guy and leaves, and then the other 2 bounce a little bit, and then the second one leaves, and it seems like the third one stays at least for a while. So a very nice work, sort of, that's a spin-off on this work that that I presented. So I'm basically getting, according to my watch, to 40 minutes. The talk's supposed to be 40, 50 minutes. I had 40 in my mind, but actually maybe 50 minutes. And I don't quite know how to show this animation now. If I leave, I don't know if anybody has an idea or
André, can I make a suggestion?
Yes, please.
Take a look in our Dropbox folder. The videos are there. Maybe you can play from there.
I don't know, but I'm going to have to share the window again. That's a problem.
Okay. Okay, I see.
It's going to take some time, and then
Okay.
people are going to be, well, thanks very much for
Okay.
the suggestion. I think I apologize. It's the first time I do a webinar. I wasn't expecting for this problem. I thought actually I had tested all of these things with George, which was quite helpful, and it worked. And now, for some reason, surprise, it is not working. So I apologize to those of you for not being able to show this. But again, in the JFM paper, supplementary material, these videos are there. And well, thank you very much for coming, and sorry for this problem here right now.
All right, let's thank Andre.